Hello, everyone, and thank you for joining us, and welcome to the latest DZone webinar. My name is Jason Cockrum, and I'm the Community Engagement Manager here at DZone, and we're really glad you joined us today. It's got a really exciting topic, and it's really relevant for a lot of us, and so we're happy that you joined us. If you're new to DZone, we are one of the world's largest online communities of software developers and experts. We publish all sorts of knowledge resources for developers and really anyone who's passionate about software development. We've got things like ref cards and trend reports and all kinds of articles written and published by our community. And all of this makes us the go-to knowledge hub for software developers all over the world. We also do a ton of great events like this one today. We've got everything from virtual roundtables to fireside chats to webinars. And who knows, you might even see us at a live event sometime in the near future. So be sure to check out our website, dzone.com/events, and you can see all of our great events right there. Today, we're going to talk a bit about this new technology that you may not have heard of called ChatGPT. As we all know, ChatGPT has essentially taken the world by storm in just a few months. And let's be honest, I think all of us wish we could have even a fraction of the adoption rate that ChatGPT has had. And since it's launched, developers all over the world have been trying it out and using it to help write code. But unfortunately, we've been finding out that the code it produces is often wrong and requires additional human input. The good news is that the large language models that power these generative AIs are not the only way to autonomously write code. Fully autonomous code writing is entirely possible without using an LLM, using something called reinforcement learning, which is something that guarantees our code will compile and run correctly and safely. And so to talk about the pros and cons of using LLMs to help write code and how reinforcement learning differs from those models is Matthew Lodge, the CEO of DiffBlue. He's been in the software industry for more than 25 years, including roles as an SVP at Anaconda and the Vice President of Cloud Services at VMware, and much more. Lastly, here at DZone, we're all about community, so I encourage you to get engaged and to get involved in the conversation today. On the right-hand side of your screen, there's a box where you can chat with other attendees and discuss your own experiences with using ChatGPT to write some of your code and whether that worked or didn't for you. And you can also submit questions there, and we'll do our best to answer as many of them as we can towards the end. So at this point, I'm going to stop talking and turn it over to Matthew. Matthew, take it away.
Great. Thanks, Jason. And thanks, everyone, for coming to the presentation today. So we're going to talk about ChatGPT. We're going to talk about that style of code generation, code suggestions using large language models. And we're also going to take a look at reinforcement learning, where that came from, who's using that, and what that looks like. So without further ado, let's get started. So essentially, we're going to look at the landscape. We're going to look at large language models in general, ChatGPT. We're going to look at reinforcement learning for code writing, and we're going to do a live demo of that so you can see exactly how that works. So ChatGPT is really cool. I've asked it to write a haiku about a software project that is very late, and it did a terrific job. It got the right number of syllables in each line. And I think this is a pretty good haiku. And this is the reason why everybody has heard about ChatGPT and why the take-up has been phenomenal, is because it's incredibly accessible and it generalizes across all kinds of different text generation, language generation tasks, including writing code. So if we think about the state of the art in generative AI for code, then we can think about code suggestion technology, unit test writing, and code optimization are really the three main groups of products and projects that exist in the industry right now. So in terms of the overall landscape. So code suggestion technology, probably the most famous is GitHub Copilot. So based on GPT-4 on the back end. So they're using large language models to make code suggestions. I would also give honorable mention to Tab9. Tab9 has been doing this for a lot longer than Copilot. They are one of the OGs of code suggestion technology, and they built their own language models to do that. And then, of course, you can use ChatGPT itself to write code outside of something like Copilot. In unit test writing, you've got us from DiffBlue. There's also an open source project called EvoSuite. We use reinforcement learning to write unit tests. And then also in the reinforcement learning camp is Google DeepMind with their AlphaDev product. And so I'll talk a little bit about each of these, and you'll see what the differences are and what they're good at, what they're not so good at, so the pros and cons. So if we think about large language models and think something like GPT-4, the T in GPT, generative pre-trained transformer, is this technology. Transformers are a form of neural network that were originally developed at Google for language translation, other language processing tasks. And so you can see how a transformer works in this translation example, going from English to French. If the quick brown fox is what we want to translate, we feed that into the transformer and we ask the transformer to predict the next word. Now, you can see that we've broken down the input into words. Now, in large language models, they're actually called tokens. And a token is roughly analogous to a word. Not exactly, but close enough for us to be able to describe it. And essentially, you're asking, so what's the next token that should come in this sequence? And the transformer then feeds that token back into itself. And so you can see as we go along, it says what's the next word that comes after le and renard, because we're talking about a fox, and le renard brun, which is, we swap the order of these tokens for French, right? The adjective comes after the noun. So you can see the transformer is just building up the response one token at a time. And that's exactly how GPT-4 and all of the large language models that use transformers, they all work this way. So OpenAI has really made this incredibly popular, as you all know. And so the history here started back with GPT-2 in February 2019. And so this is early versions of Tab 9's product used GPT-2 before they developed their own, for example. This was an open source model. So both the source code for the model itself, how you train it, inference, all of that was open source, along with the data, so the weights for that model. It's big, like 1.5 billion parameters was pretty big, even at the time. If you, by contrast, if you think about neural networks that are used for image recognition, so ImageNet, which was a neural network that can recognize images off the internet, and it's more accurate than a human at doing that, is a roughly 0.5 billion parameters, so 500 million parameter model. So that one was pretty big. So GPT-2 was already 3 times bigger, and demonstrated it could translate text and summarize and answers questions. And then we've got GPT-3, which was the big breakthrough in July of 2020. So we're looking at this in a very short space of time. Then we got a much better model. Closed source, though, this time. So the data in the source code not available, much bigger, 175 billion parameters. GPT 3.5 in November of 22, also 175 billion parameters, also closed source. Also incorporated what they call reinforcement learning by human feedback, RLHF, some additional fine tuning, and I'll talk about that in a second. And you can see that these models got better and better, and this is really where the excitement came from. Small mention, Codex was the first model used by Copilot. That was a derivative of GPT-3, which essentially has been abandoned. So Copilot now uses GPT-4 as the back end as of March of this year. So just to give you an idea about how massive these models are, then you can see that the amount of compute you need, the number of flops, floating point operations, to train is very, very large, 3.14 times 10 to the 23. To give you some idea of how much that is, if you used a single NVIDIA V100 GPU to train it, it would take 355 years to train. And of course, nobody does that. It's trained on a large cluster of GPUs, but it gives you some idea of the massive amount of compute resources required. The folks at Lambda Labs estimated what this would cost to do on Azure, about 4.6 million for a training run. So that gives you some idea of like the massive scale. And so this was also some of the controversy about large language models, not only because they're now closed source, but also if you don't have very deep pockets, you can't play this game. So it looked like only the people with lots of money would be able to do that. Now that's turned out not to be true. And I'll talk about that a little bit later on because of fine tuning. But it gives you some idea of just how big these models are in order to be able to do what they do. This is what we know about GPT-4. So this is my joke slide. It's a black box. So when GPT-4 came out, OpenAI decided they didn't need to tell us anything about the model for commercial reasons. They thought this would hurt their competitiveness in the marketplace. So we don't know how big it is. We don't know how it was trained. We don't know what it was trained on. I think it's safe to assume that it's not smaller than GPT 3.5, but we really don't know very much about it. However, back when GPT-3 was released, OpenAI did a really good paper looking into the pros and cons of this kind of approach. And the interesting thing about these pros and cons is that they're consistent across the evolution of these large language models. In other words, the problems are the same as the models get larger. They don't go away just because the model gets larger. The strengths are also the same as the models get larger. So the thing that really got people excited about this was that large language models gave a really good answer in one shot, right? You give it one prompt and you get a really good response most of the time from a large language model. And these models could do text generation tasks they had not been explicitly trained to do, right? So these language tasks, it would generalize across these different language tasks. Nobody trained GPT-4 to write haikus, right? That wasn't a specific training task. It has learned how to write haikus because it's seen lots of them, and it has learned the patterns, the statistical text patterns for haikus. And so people got excited about this because this generalization was something new. Previously, when you'd had neural networks, they were trained for one specific task, like image recognition. And if you gave them a slightly different task, they couldn't help you. They didn't work. So the third point was the results from these more general tasks were comparable in accuracy to explicitly trained language models. So they generalized, and they were just as good or close to it being as good as a model that we trained explicitly. So this got everybody very excited. So what this means in the context of code is, for example, things like boilerplate completions, right? So in this example here, you're doing all the boilerplate for a class definition in Java. The really important part of this is that comment at the top. A person, class with a name and age accessors and the equals and hash code. That is the prompt that's going into the model on the back end, and along with public class person, open curly bracket, right? So that little fragment of code plus the comment. And so what it's doing is the model is guessing what comes next. And it's the rest of the class definition. And it's keying off that information that's in the prompt. The more richness you have in the prompt, the better these models will do. And so you can see it does a really good job of putting all of the basic stuff in this class. Another example is calling into foreign lands. This is when you're calling an API. It's probably not something you write code for very often. You would typically go look at the API documentation. You might try and find some examples, maybe look on Stack Overflow for an example of some code to do this. And now you can have something like Copilot or a large language model, Tab9, suggest to you a completion, something that it has learned. This is an example in Go, but you can see exactly how this works. And you can see that this, although it's not exactly correct, is close enough. You can take this and you can modify it, and you get a decent result. And traffic to Stack Overflow has gone down since ChatGPT came out. And obviously correlation is not causation, but maybe that's the role of this kind of tool. So OpenAI was also very honest about some of the weaknesses of GPT-3. And again, these weaknesses persist across the models. Drawing factual conclusions was not its strong point, which makes sense if you think about it. Essentially, what these models are doing is learning statistical text patterns. They see lots and lots of text, and essentially they're looking at what's the probability that the next word is this, right? So they learn the probabilities from the training data, and they use those probabilities then to generate new text. So whether that's factual or not is really not something the algorithm is concerned about. It's not something it knows. All it knows is what's the probability of the next word, right? It knows the probabilities of all of the next words, and it picks one. Similarly, non-language tasks like maths or math, if you're American, is not typically a language task. And so particularly for multiple digit math, and higher order mathematical functions, large language models don't do a good job. That's not really a language task. repetition, lack of coherence, this is called hallucination. The idea of sort of losing the plot. If it doesn't have a good set of probabilities for what comes next, then you can get these very strange completions, fantasies, incorrect information. The fourth point is that these models are inherently unpredictable. They are massive statistical models. Very small changes in the prompt can make very big difference to the output. It's why I believe that prompt engineering is not a thing, really, in the sense that it's not engineering. You obviously can put more information into a prompt and get a better outcome, but you can't predict what kind of outcome you're going to be. It's not like there's the idea that if you make a change to the prompt, then you'll be able to predict what that will do to the output. It's trial and error for the most part. And so the main thing to remember is that it's just a statistical model of text patterns. So if we apply that to unit test writing, then you've got a couple of examples here, just to illustrate some of these points. And the first one is we have a Java unit test for an add method that doesn't do anything. So we just call it add, it takes in 2 integers, but there's no body to this function. And so when we ask GPT 3.5 for a unit test to match that, it's great. But this example doesn't add. And so this unit test would not pass. Now, this is a somewhat contrived example, you might say. It's like, well, who does this in the real world? The point we're trying to make here is that it's all about the text. It's keying off the fact that this is an add function, so that's what it thinks it does. It's just going off the text and using that to do a prediction, and it does a good job actually of a unit test there. Here's an example of how this persists across versions. GPT-4 makes exactly the same error. It does it much more eloquently, but it's still wrong. So what's in the text really matters, not what the code does. You know, we can play with this a little bit more. Here we have an add that multiplies, same problem. And then on this particular example, we did a saturating add. So this is often used actually in machine learning, but essentially you're going to sum 2 numbers. And if it's greater than 100, you're going to return 100. And if it's less than minus 100, you return minus 100. And we get hallucination. We get a test that makes no sense. It calls some method that doesn't exist. And this test, would not compile. And it's essentially junk. And so you can see just small changes to the input there produced a very, very different result. So one of the things that is in ChatGPT 4 and was in 3.5 is this notion of reinforcement learning with human feedback. And so what does that mean? Essentially what is happening here is you're fine-tuning the model to prefer some answers over others. And so in this example, we can have a sentence. We're going to go for a completion of a sentence. Citizen Kane is, and then here are 4 possible completions that you could give for that sentence. One of the greatest movies ever made. That's my opinion. A commercial failure. That's a true thing. It really was a commercial failure. The end of Orson Welles' Hollywood career. That's also true. That happened. And then somebody at the time who was, a big fan of the target of the satire that is Citizen Kane, said it was a vicious attack on a great. A vicious and irresponsible attack on a great man. So essentially what you do in this situation is you rank those answers and you essentially are training the algorithm to prefer some answers over others. And this is useful in the case where for correcting hallucinations, if the model is gone completely off the rails, you can train it to give a better answer this way. This is also why if you see prior examples where maybe GPT-3 didn't do a very good job on a particular example, GPT-4 has been trained on the best answer for that. And you can see that if you run those examples back through again. So some human has written answers. And that's the other thing, as well as ranking, they have humans write answers. And so this fine-tuning approach is a nice way of using human intelligence to augment what the model does and sort of putting the two together. And it can makes the model do a better job. Some examples of how it can be quite difficult to spot the errors in the code. Now, I used to be a software developer. Nobody would pay me to write code these days. It's been a while. I had ChatGPT 4 write me a Python function for a perceptron. Perceptron is one of the building blocks of neural networks. Essentially, you're training a recognizer with this. And so there's a fitting function and there's a prediction function. The fit function is how you train it to recognize, to learn exactly how to recognize the data. And then your prediction function is there. You can see essentially you're multiplying the weights by the input and giving a result between 1 and -1 if the data that's being input matches the recognizer. So I'm not a developer anymore, but there are 2 bugs that I can see in this code. And the first one is that this perceptron will never learn. And it's quite subtle because it's basically down here. You're multiplying by x at the inside in the inner loop of this fit function down here, and x represents the weights. And the weights are set to 0 here in the initializer for this class. So this perceptron will never learn because the weights are always 0. The other thing that it doesn't do is it doesn't normalize the input. And so if you feed data into the fitting function that is on different scales, it won't learn correctly. So that gives you an idea about how difficult sometimes it can be to spot the error. So this looks, at first glance, this looks really good. But the monitoring task can be quite difficult for reviewing the code. And that's one of the downsides. Even though the code is very good, it's close to being right, it can be quite hard to spot the difference. And then there's a flat out misinformation. This is a really extraordinary example. So where ChatGPT generated hallucinatory Python to call an API that purported to, given a phone number, to be able to tell you where that phone was, which is a scary prospect if you think about it. Somebody could just take your phone number and know where you were. That's not really information that you necessarily want everybody to have. The amazing thing about this is that the API that they were calling has never offered that capability. OpenCage is a geolocation service, so you can take a street address and it will give you GPS coordinates, or you can give it GPS coordinates and it will give you a street address. So it's used in lots of different applications. They've never offered mobile phone geolocation, but all they knew was they saw a surge in signups for their service and then a wave of cancellations and bad reviews, and they had no idea why that was happening. They've never claimed to offer this service. And it turned out that this was code written by ChatGPT. They finally were able to track it down. So it's an example of how this hallucination can lead you astray. So the main thing to remember about large language models is all about the text. And what matters most is the text in the prompt and the text in the training. So large language models don't really understand anything. They just learn text patterns. You get hallucinations when the training is thin and it doesn't have good probabilities to use for prediction, or if there's not enough text in the prompt. And also, because of the way it's trained, it will never write text that hasn't been encoded in training, right? So, for example, in a coding context, if you've got internal libraries that you use at your organization, it's never going to write code to call those because it's never seen that code before, right? And then large language models are the same regardless of model size. So the kind of problems that we see with large language models, there are papers back from 2014 and earlier that talk about some of these issues well before large language models came along, well before GPT-2. So it's all about the text. Now, one of the things that we've been told about, there's some papers, there's a paper from Microsoft that talks about sparks of general intelligence using large language models and ChatGPT. Jeff Hinton, who at the time was a Google fellow, Jeff is one of the people that invented back propagation, one of the most important methods used for training neural networks. So Jeff pointed out in an interview that we learn to throw a basketball so that it goes through the hoop. That's how we do it. We practice. We don't learn that using language. We learn it by trial and error. So the person on the left in that photograph is not learning to play basketball. The people on the right are learning to play basketball. And this is a really important distinction. And this leads me on to reinforcement learning. Reinforcement learning is learning by trying to throw the ball through the hoop. So if we look at unit test writing and code optimization, these are two of the best examples for reinforcement learning for coding today. So DiffBlue, that's what we use for unit test writing. And then Google DeepMind a couple of weeks ago announced AlphaDev. So in the case of unit test writing, we are writing unit tests autonomously for Java applications by searching for those unit tests. That's essentially what's going on. And it's very fast. It's about 1.5 seconds for us to write a unit test. So much faster than a human. Code optimization, what is happening is that AlphaDev is finding more efficient implementations of existing algorithms, and really important algorithms like sort. Right? So what they did for the sort function in the C++ library is they got between 1.7 and 70% efficiency improvement, which is pretty useful given how often the sort function is called. So we're going to, both of these approaches search for code. And so we're going to explore both of these and see how that works. Now, reinforcement learning has been very popular in AI for game playing. So it's the strategy used by AlphaGo. And the whole idea with AlphaGo is that there are more moves in Go than it is possible to look at. You can't just evaluate all the possible moves in a game of Go and figure out which one is the best one because there are just too many. This is unlike chess. Chess does not have as many possible moves, and the latest and greatest chess software just looks at all the possible moves at any point in the game. IBM Deep Blue essentially used that approach, and they did that first well over 25 years ago. So you can't brute force, you need to go search for the best moves. So how do you do that? So reinforcement learning essentially implements probabilistic search. You identify areas of the solution space where those solutions are likely, and you spend more time looking there, and you ignore the other portions of the search space. Reinforcement learning is the algorithm that guides that search. So writing code is very similar to finding Go moves. You can approach it like a game. So in AlphaDev, winning, like in winning a Go game, winning for AlphaDev is an algorithm that takes less time to get the same output. Winning for cover, our product is unit tests with 100% coverage that find regressions. So you can think of those as that's the function, that's the thing you're trying to optimize. So essentially, we have a few seconds to play, learn the rules, and win the game. So here's what AlphaDev did for the sort improvement. So they ran it on the assembly language instructions. They ran on x86 assembler. And you can see that on the left-hand side, the original implementation, and on the right-hand side, the version that AlphaDev came up against. Essentially what it did is it tried deleting instructions, it tried changing the assembler language instructions, moving things around. It tried lots of different ways to see which of those approaches would improve the algorithm. Would it get the same result? And was it any faster? And so you can see that the changes are very small, quite subtle, right? So they removed a move instruction. So you saved a little bit of time there. And then the min function, instead of being ABC, is just A and B, as it turns out. But those small changes are enough to drive, a really significant improvement in the sort algorithm. So the way that works as reinforcement learning, essentially what you do is you predict what better code is. And so in the case of AlphaDev, they're trying different mutations of the code, you think about it that way. They assemble it, they run it, and they look at the execution time and the result. And so they evaluate the effectiveness, like, was the output correct? Was it faster? Things like that. From that, they can predict what some better code is, right? So maybe taking out that move instruction was a good thing. Now, what happens if we change something else? So they're iterating through different alternatives, different sequences of instructions, running those and finding a better solution. So that's what they did with AlphaDev. So it essentially is really good for optimizing frequently run a library code. So they did a paper in Nature about this. So sorting, hashing is where they got started. They can find essentially new implementation of common algorithms, right? So the machine finds a better way to do things than a human does. And that's also super useful for research. So when we, at Diffblue, when we do test writing, we've been using the same approach now since 2019. And essentially we're doing the same thing. We're conducting a search. You can think about it of the set of all possible unit tests for a particular method. We want tests that are valid and run, get high coverage, that developers find easy to read. Because developers obviously have to look at the code. When a test fails, they need to very quickly look at the code, understand what it does, figure out what to do. So the way that our product works is that we can write a unit test baseline for the entire application. So we can use that reinforcement learning approach to write tests for the entire application completely autonomously. I'll get into that, how we do that in a second. So that when you implement a change, then the unit tests will tell you about potential regressions, right? The behavior, if the unit tests fail, it means the behavior of that unit has changed. And the developers can either fix the code or that maybe they need new tests. The reason that the test is failing is because the code is something different now. And so they can just take new tests that have been written against the new code. And that is the update of the baseline. So our product gives you that set of tests to begin with, and then it maintains and iterates and improves the unit tests as the code base moves along. So consistently writing tests is actually much harder than code completion because it requires context that isn't in the code, or often isn't in the code, before and after the insertion point, right? When you're doing using an interactive code suggestion tool, it's got the chunk of code before, the chunk of code after, and it's trying to guess what goes in the middle. And oftentimes there are methods, factories, things, literals, things that you need in order to write a unit test that aren't there. They're elsewhere in the program. Second thing is that you need a semantic model of the program to be consistently correct. If we want to do this so that a human doesn't have to look at everything and try and figure out if there are any bugs in it, then you must have a semantic model of the program. And that's much more valuable when it's 100% autonomous, right? Because you're not requiring somebody to do a monitoring task and check every single thing. So the way Diffblue works is that we do some analysis of the program, and we take a look at the code, and we guess what the first test should be. What's a good test? So based on the signature and the analysis that we've done, we compile and run that test, and we look at the results. How did it do? What result did it get? Did it throw an exception? Did it get, how much coverage did it make? Other metrics about the effectiveness of the unit test. And that gives us information that allows us to predict what a better test would look like. So we try something else. We write that test, we run it, we see how it does, and we iterate through this loop. And we can usually get approximately 10,000 iterations in about 1.5 seconds. So you can see how that search is conducted. So in a typical software change process, it looks like this. You've got running code, the engineer writes a change, they create a pull request in Git parlance. They run the unit tests, and based on that, they decide, is this PR ready to go? Maybe there's some additional human review, and then eventually the engineer either makes changes to the code or the PR is approved. So a Diffblue cover, essentially you've got that test baseline that we've written from the initial set of working code. So you can run those unit tests along with any human tests that have been written as part of the PR process. And then once the PR has been approved, the engineers either updated the code or they need new tests, then we can update the baseline by essentially rewriting the tests that are affected by a particular pull request. So it works incrementally. It doesn't rewrite all of the tests. It rewrites just the tests that reach the code that was changed in the PR. So with that, what I'm going to do is I'm going to do a demo. So I'm going to stop sharing for a second so that I can switch over and share a different window on my system. So hold tight. Right, so the first thing I'm going to do here is share Pet Clinic. So here we are. This is Spring Pet Clinic. This is the example application I'm going to use. This is from Spring Java. It's an example application that implements a vet's office. You can see with a cute picture there. One of the things we can do in the vet's office is we can go looking for owners. So if I don't enter anything, I get the full list of owners. It's nicely paginated. That's all great. If I enter, let's see, Davis, and I hit find owner, we've got 2 owners with last name of Davis. And so we get, again, nice paginated list for those two owners. If I put in an owner where there's only one result, we get a nice little optimization here. So we go straight to the page for that owner. It doesn't give us a list with just one item in it. It gives us the just straight to the owner record, right? So that's a nice thing for it to do. So that's the case where we have exactly one. And then if I put in my own name, then it's not found, right? So again, error message, and we get back to the search form, essentially redirected to the place we came from. So that's the logic that we are going to test. And so I'm going to just switch back again. Bear with me. So here's the Java code for that. So you can see there's 4 cases that I just went through. We've got the empty field case. We've got the not found case. We have exactly one result, right, where we check for total elements being 1, and we go to the page for that plus the owner ID. And then 2 plus owners, we show the list, right? So that's the Java code that implements what you just saw. And what we're going to do is switch over into IntelliJ, and we're going to have a look at how DiffBlueCover writes some tests for that. So what I'm going to do right now is switch over to IntelliJ. So here we are. I'm going to run DiffBlueCover. It runs entirely locally on this machine, right? There is no cloud service running here. This is a Mac. It's a MacBook Pro with an M1 Apple Silicon processor in it. You can try this at home. So this, I'm going to use the community edition of DiffBlueCover. You can download that from the IntelliJ marketplace and just search for DiffBlue. When you install it, and so you get this menu at the top here, but you also get this little Flask icon. So if I hover over that for a second, so I can click on that and it will write the tests for this particular method. So let's do that. And off it goes. So again, this is running entirely locally. That went fairly quickly. We do an environment check. We want to, what build system is this? What version of Java? All the other things, so that we can write correct Java code, right? It's no good as writing JUnit 4 if you've got JUnit 5. Well, so we need to know all this information. We get that from the environment, so the product basically configures itself. And then we get into writing tests here. And let's see how long that takes. It should be done in just a few more seconds. There we go, 4 tests. So start to finish, that took us just over 30 seconds. That included running Maven to get the build information, by the way. And so now we can see that those tests live in the project over here. So they've shown up. There's a new file called owner controller test. It's orange because IntelliJ has noticed it's just popped into existence. And so I can double click on that and we can go look at these tests. So this is the code that's been written by DiffBlueCover. It would help if I move that out of the way. There we go. And so we've got our unit test JUnit class here, and taking a full advantage of what Spring Java provides us in terms of mocking. Spring Java's got really great support for unit testing. And makes this pretty straightforward. So the first thing we're going to do here, the important stuff, is this when-then statement where we're mocking out the database, right? So Pet Clinic calls a database that's got the owner information in it. By default, we're going to mock that out. And instead, in this first test, we're going to return the empty array list, right? So we've got nothing. That's going to trigger that first case there. And then you can see we basically run a couple of mocks here. Again, we're mocking out the front end, the web server. So we're going to call that controller by running mock MVC builder, right? And we build the request and we perform it. And then we are essentially looking for, to check what comes back, all right? So is this doing the right thing? So in this case where there's an empty list, we want to see that that was okay, that the code ran correctly, and we got redirected back to the find owners page. So that's covered the first case. The second case is where we have exactly one owner. And so here what we're doing is constructing the mock for an owner record. So we create a fake owner record for Jane Doe, who lives in Oxford, obviously, because we're from Oxford. And so we create an array list, and then basically create the right object to return. We've got the when then statement, so we're going to return this object instead of going to the database. Same kind of approach, bunch of mocks, call the controller, and check that the attribute exists. So this we got an owner record back, and it's owner 1, right? So the redirect is taking us to the owner page for owner ID 1 that we set up here. And then the third test, you're getting the idea now. We create 2 owners, we return that. And so we check here that we get a page that's got all of the right items on it. It's got this pagination and so on. We get a list of owners, right? So we're on the owners list page. We didn't get in order to, with these items on it. So we found the right things here. And then the final case where we don't return anything, but we search for dough, and that's testing the example where we've got name not found. All right, so we go back to the find owners page. So you can see how this approach can be very effective at finding unit tests. It's a very powerful technique. So just switch back to the presentation. So what is Diffbot Cover good for? It's good for autonomous Java unit testing. We only support Java today. We picked Java as the language because it's been, one of the top enterprise programming languages for the last 25 years. We will do other languages in the future. We developed the product so that it would, we could be successful with one, and we designed it in a way, we architected it in a way that we can add additional languages over time. It's really great at doing autonomous unit test maintenance. There's a dashboard for coverage, real and bias risk, and that's all it does. So essentially what we have done with something like Cover is we've traded the generality of large language models approach for something that's more specific, but can be much, much more accurate. So we have customers today with million-line Java applications. They can run Cover against that application, and they do run Cover against that application, and then they get tens of thousands of tests. And so it's a very different scale of operation. Customers typically integrate the product directly into their CI/CD system. They're not writing one test at a time. They just make it part of the standard way that their developers work. They just get the Diffbot tests, and they can decide what to do with them. Right? They don't have to run anything. They don't have to mess around in the IDE. And so that's it. That's my summary slide. We looked at generative AI for tools. We look at some very general tools like ChatGPT, Copilot, and the like. All of this stuff is real. It's available today. You can try it. And all of it helps to improve developer productivity and help eliminate tedious and error-prone coding. Reinforcement learning is just vastly better than large language models for unit test generation because it is a focused technique. It's a search technique. It's goal-seeking. It's looking for the outcome that you want, as opposed to trying to be a more general tool. So it solves a narrower problem, but solves it in a much more accurate way. You can try all this. As I mentioned, there's community edition if you use IntelliJ. If you don't use IntelliJ or you want to try the command line, we've got this QR code right here. There's the bit.ly link there, and you can just try it. Enter your email address. We'll send you a link to download the code plus a license key, and off you go. And you can just try it yourself. So with that, I will stop and ask if there are any questions.
All right. Thank you so much for that, Matthew. This has been quite engaging. Definitely been quite a lot of interest in this. So this is a fascinating topic. And I was impressed, honestly. So thank you very much. We do have some questions. We'll try to get as many as we can in the next 10, 15 minutes or so. So bear with me here. First one, I think going back to the Citizen Kane example from the presentation. Basically, when you place a human in the loop, right, how do we detect human bias? Or in the case of like actual code preferences, for example, like, what is a woman, right? How do we detect the actual human bias? How do we account for that?
Well, so part of the challenge is that you don't know. You don't know if the answer was generated directly by the model and or it's been trained on a human answer, because it's all essentially in the training set, that fine tuning that goes on. I gave the example with Citizen Kane. I mean, essentially what it's doing is tweaking the weights in the model, right, to prefer some answers over others. And so you can't tell the difference between a human written answer and one that came directly from the model.
All right. Thank you. Okay, another one about the, I think this was with the basketball example. And we were talking about how large language models don't understand what your program does. It just learns text patterns.
Yes.
The question was kind of pushing back a little bit about that, specifically with what about like emergent things like maps from descriptions seen in GPT-4?
Yeah. So there's a really great paper from some researchers at Stanford that basically said nobody has demonstrated any emergent behavior in GPT-4. So a couple of folks have asserted that there is emergent behavior. The view from researchers is that there isn't. There is no emergent behavior. Okay,
good to know. All right. Okay, how do I make use of large language models or ChatGPT or something like that in household data analytics and data storytelling?
Wow. I don't know, actually. I think that's the honest answer here. I mean, I can think of, I would be making it up on the spot, right? I can think of ways it could be used, but that is not my area of expertise. So I'm afraid I'm going to have to say I don't know.
That's all right. Well, hey, maybe we could put the question into ChatGPT and see how it answers. Ask it itself. Okay, another one here. Any details about how much of the tech debt has been handled and how it was measured with this tool, and what tools used to show the advantage? Like how much of the tech debt has been removed by using DiffBlue? Is there any way to measure that?
Yeah, there is. So essentially, the two ways that most of our customers look at this is, everybody looks at coverage. So how much coverage are they getting from the unit test? So how much code is being exercised? The coverage just doesn't tell you the whole story, right? Because if you're not checking for the correct behavior in the program, you can have 100% coverage and not check any behaviors, right? So coverage is not the full story. The other thing they look at is like, what do the tests do and are they any good? And so some of that is just by looking at them. So when they test the product, they spend a lot of time inspecting the tests and seeing what it's produced and making sure it's doing a good job. The other approach that we've seen people use is to run mutation testing. So they mutate their program and they see how many of those regressions are caught by the unit tests. And that gives them a quantitative answer to that question.
All right, thank you. Okay, another one. I think I can answer this one actually. When using DiffBlue, will any code be sent to a server outside my organization? If I remember correctly, you said it's all on-prem, like it's all local. Yes. So there's nothing that's sent off. Yeah, so no code leaves. We do have telemetry, so we understand how people use the product, but you can turn that off as well, right? It's an option. Okay. Yep. And actually, so I had a few people ask this question. You did mention that it's only for Java at the moment, but we've had a lot of people asking, are you planning, are you hoping to expand this to other languages in the future? Yeah, absolutely. So we're working on the second language right now, in fact. Yes, so we will do other languages in the future. Okay, cool. Good to know. Okay. We've got another one here. How much time do I need to spend on reviewing the tests that DiffBlue writes? Like, how do I know they're good? And then a kind of a follow-on question to this too, I think, or tangentially, is if the code I'm writing has a bug, will that be reflected in the test? Like, can DiffBlue pull that out of the test, if that makes sense? Yeah, it does make sense, yes. So let's handle the first question, the first part of that. So how do I know the tests are good? So it's a very similar answer to the question earlier. How do I know what sort of tech debt and what effect has DiffBlue had? So the main way that people do that is they, early on when they try the product, spend a lot of time looking at the tests. And so they essentially get comfortable with the kind of test that we write, and they start to understand that. And they look at a lot of those and they get comfortable with what we're doing. People who want a quantitative answer use things like mutation testing, or they essentially make changes to their applications and they see if are the unit tests doing anything. So they test it. That's how they do it. And then the second question is like, well, my application has a bug, and so you're going to write a unit test that reflects this bug in my application. And that's absolutely true. The only thing we know is what the application does. We don't know the intent of the application. However, you've got to remember that the purpose of unit tests is to find regressions, right? So by definition, your unit test should pass.
when running against your code, right? So human unit tests do the same thing, right? It's human written unit tests. You write a unit test, it reflects that bug in your code. And if humans wrote all of your unit tests for your application instead of DiffBlue, you would have a set of unit tests that passed that reflected that bug. That's exactly where you would be. The reason it matters, and the reason why that's okay, and the reason why it's important is because you ship that application, typically it's doing work, useful work somewhere. And so everything that touches that application depends on the behavior of the application, not what you intended. Right. So knowing about changes in the behavior application, even if it has bugs, is incredibly important. Right. And so understanding there's been a change in behavior is useful because other systems depend on that. And maybe they depend on your bug, or maybe they've got workarounds for that particular bug already coded into them. So it's really important to know when the behavior changes. It's less important for the code itself to be completely bug-free because essentially you're running this against code that is good enough to ship, right? And it's presumably working and hard-working code, and it's doing useful things already.
Good to know. Okay, let me see. I think we got a couple others. How does DiffBlue handle mocking?
So essentially, the tool product looks to automatically mock. So it creates the mock for you. And we use the mocking that's built into the framework. So you can, in the case of Spring Java, there are standard ways to do mocking. So we follow those, right? And Spring Java makes it a lot easier for us to construct mocks simply because of the structure that the framework gives you. If it's not Spring Java, then we're essentially figuring out what the mocks should be. We can't always get that exactly right in a regular Java, so you can also steer the product, you can guide it into what to mock.
Good to know. Okay, let's see here. Can you say anything about the underlying tech of DiffBlue, like program search or Dreamcoder? Like, can you talk, is there anything you can share with us a little bit more about how that works?
Yeah, so we have a couple of blog posts where we get into a little bit more detail, but it is essentially, what I said before. You think about what's our secret sauce. It's really in two things. It's in the, how we analyze the output and sort of the reward function and sort of figure out how to steer to get better tests. And it's in our test predictor, right? So how do we generate those additional tests? The reinforcement learning, all reinforcement learning algorithms look the same, right? They generate a candidate, they apply the candidate to the environment. In the case of Go, they make the move. In the case of us, we run the test. And then they look at the results, and based on the reward function, as it's called in reinforcement learning terminology, then they feed that into a predictor to generate the next iteration and go around. Essentially, you're trying different things. You're following things that work well. You may backtrack on things that stop working so well and try a different path. That's essentially what's going on.
Okay, cool. Let me see. I think we might have time for a couple more. Sorry, try to keep an eye on the time a little bit.
Yep.
Somebody was asking, maybe some more clarifying with the Go example of how the AI selects the regions to basically go investigate, like how it chooses which regions to focus on and which regions not to focus on.
Yeah, so in the Go example, essentially what it's trying to do is it uses a prediction about who's going to win the game. And that is the main way that it steers itself into those. That's how it finds those areas where the solutions are more likely to be found. So if it finds it's heading into it's going down a move path where the chance of winning the game is getting lower and lower and lower, then it decides that this is a not such a great area to explore, and it will try a different area. And that's essentially what AlphaGo is doing.
Okay, cool. Let's see. One other question here. Okay, when talking about like writing the tests and kind of just in general and stuff like that, question is, have you tried the reverse? Essentially manually writing the unit tests and then generate the code to pass those tests, or the automated test development?
Yeah, I mean, we can certainly do that, because you could use exactly the same approach. We have not done that, but yeah, that is absolutely possible. You could go the other way, because the same search approach would absolutely work.
Interesting. Good to know. Just a few more minutes here. I think we got time for maybe one more.
Yeah.
Follow-up question, kind of what we were talking about. There was a portion of the presentation where it implied that it chooses tests that are human readable automatically, right? That are instantly human readable. So how does it determine readability? Like, how does it determine what can be read by humans?
Yeah. Okay. So that's a great question. So that slide, I'm sort of talking about a Venn diagram of sort of like, what's the subset of tests that you want to, the area you want to explore, essentially. The way that we do that in the product is that when we're writing candidate tests and seeing how well they do, the thing that generates the code for those tests, the Java code generator, is written to mimic human patterns. So we actually have a patent on this. So if you really want to know, you can go look at the DiffBlue patent for human-like test generation, and we tell you exactly how we do it. In that patent is that you go to the USPTO site.
Okay, good to know. Okay, so I think, let me see, we might have one more through. Okay, this is a good one. Is there a white paper, either you guys or somebody else you could point to, on reinforcement learning for software testing, that people could reference, or somewhere that you guys could share?
So there is. I think the other thing to point out, there's an O'Reilly book on reinforcement learning.
Okay.
Very well written by another English guy. But don't hold that against him. And yeah, it's very good. Phil Winder is the author, and it's a really good introduction to reinforcement learning for lots of different applications. And then I can certainly dig out some more specifically reinforcement learning for unit testing. I've got some white papers on that, and
okay.
I can post those.
Okay, wonderful. We are kind of pushing up towards our time, but definitely still getting a lot of engagement, a lot of great questions. And so I encourage everybody, if we didn't get a chance to get to your question, or you still have questions, feel free to reach out. You got the QR code on your screen. You can download the free trial. Go to the DiffBlue website. I'm sure there's ways to get in touch with them there. You can see you've got Matthew and DiffBlue's Twitter handles on there as well. So definitely encourage you guys to reach out. This has been a really engaging topic, quite a lot of engagement. So very, very excited to see that. I think that's probably going to be all the questions we have time for today. But I do want to thank you very much, Matthew, for joining us. It's been quite a fun experience learning about all this stuff. This is really, really cool. Thank you, everyone else, for joining us. Glad you could make it with us. Don't forget to check out our website as well, dzone.com/events. We've got all kinds of webinars up there. And also to let everyone here know, you will be receiving the recording of this webinar as well as the presentation, so you can always refer back to it. And it'll be available on our website after this point, so you can refer colleagues to it. You can download it and send it wherever you need to do. So don't worry about all that. Thank you again, everyone, so much for being here. We're glad you could join us. Have a wonderful rest of your week, and we will see everyone next time. Thank you so much.
Thanks, Jason. Thanks very much.